Isn't that exciting? Get physics over and done with. So it'll be 8 a.m. And because of that, because we're going to work on torque here today, we'll work on torque on Friday as well. Torque and angular momentum. We'll see how far we get. That gets me to, after this week, I only have 4 lectures left. And because I only have 4 lectures left, I don't want to take up one of those lecture times for a test. So, but I do want to give you guys a rotational motion test so you have it prepared for the final. And what I will do is I'm going to do it online. I will release it on Wednesday, and it will be due by 11:59 Friday night. So I'll release it Wednesday morning, and it'll be due 11:59 Friday night, and it'll be over chapters 7 and 8. So it's all this rotational motion, center of mass, center of gravity, all of that. It's likely to be on Blackboard, so it'll be multiple choice like what we've been doing. And if you want partial credit, you can take a picture of your work and send me your work. Okay? So that's how we'll fit in the next test. If you are on the Tonkawa side, I believe that Mr. Grimm said he's going to get everything done this week because he's leaving as of next week, I think. He's not going to be around. And have you guys done the egg drop yet over there in Enid? Yeah. And are the reports due this week or are the reports due the following week?
They were due last 2 weeks.
I can't hear you. So are reports due after Thanksgiving or before Thanksgiving?
Before. They were already due.
Okay, so everybody's done with lab. Yahoo! So as soon as I get the lab grades in, I will get them into Blackboard, and later today or tomorrow, I'll be looking at the last WebAssigns. I think we've got everything open for WebAssign. I think everything's out there. You have one more quiz in WebAssign, and that's the quiz that says Prep for Final, and that will be harder than the final, I promise. And that's the one that I don't drop. That's the quiz that I don't drop because that's what I use for assessment and make sure that we have all the right stuff in for assessment. So hopefully you guys know exactly where you are. Also look at the percent. You look at 2 things to remember. One is my grading scale is not your typical grading scale. And you'll want to look at it and look at the percent for grade. And the percent for grade already includes the dropped quizzes as in there. So all of that's there. So hopefully that'll get you guys covered. And for everybody who just kind of walked in, I don't know what happened on Friday, but the lecture, I have a file. So the lecture recorded, but it obviously didn't close out correctly. And so when I try to open the file is corrupted. It won't let me open the file from last Friday. So
this is Margaret in Enid.
Yes, ma'am.
And I have the exam final schedule in front of me here. And it says that Monday, December the 10th, our exam will be at 8:30.
Oh, at 8:30? Okay.
And it'll be 8:30 to 10:20.
Gotcha. Thanks. I just knew it was the first one up.
Yep, it's the first one up.
Yep, the first one up. So we will be getting going. All right. So now that we got that stuff done, the document camera doing its thing. Okay, we got it. All right. So on Friday, we started talking about torque being a little different. And kind of where we were leaving off is I had done the teeter-totter. I've done our teeter-totter here. I've got my fulcrum. And we're going to set this up at L. And we're going to set this up at 2L. Oh, yeah, you may want to, yeah. And then we've got a force being applied. And so we had set that part up. And I kind of described it as if I have a point P, this is a vector R, and we've got our force being applied here. and we defined this lovely as torque. And we said that it was going to be a cross product or a vector product. That's where we're going to end up with is a vector product. So remember, work was force dot product of these two vectors. And that also could be this way, just so you guys know. Those are equal. And this was a scalar product. And the units, well, they were Newton meters. We actually defined that as a joule. Now, when we get to torque, that's not what we get. All right. Torque, we're going to end up with a Newton meter. And why they do this, I don't know, because we actually do the cross product like that. In the English system, we actually write it correctly. In the English system, we actually talk about it as foot-pounds. So why they actually in the metric system decide to flip-flop it, I have no idea. But this Newton meters is not that Newton meters. This Newton meters is torque. That Newton meters is joules. This comes from a dot product. This comes from a vector product. And we also said that this vector product, because of how we do a vector product, is not equal to this. Because we have to worry about direction. And then we talk about the right-hand rule. So in my right-hand rule, if I am applying a torque, my fingers are going to curl and my thumb comes out of the board, okay? That's going in this direction. That we consider positive. So counterclockwise is positive. Clockwise is negative. And if I do clockwise, I'm going into the paper. If I do counterclockwise, I'm coming out of the paper. Oh, that's where we had left on Friday. We did one more thing on Friday, is if I'm looking at my vector, so here's my R, and if I have a force applied, my forces can look like this, because we've done these before. I have a force parallel, and I have a force perpendicular. And to get the maximum torque, that's going to be the distance times the force perpendicular. That's going to give me my maximum force that's out there. Okay? And we had also said that the magnitude of my force is going to be R, F, sine theta. And how that looks is if I have my vector R and I have the force applied, this is the angle that I'm looking at for that sine theta. So I have a vector product and a cross product. Couple of things. We actually talked about the tire iron problem a little bit. Remember, I can slide vectors around. So just kind of another way to look at this. If I have this force here, I can actually slide it over here. And if I look at this angle is equal to that angle. And I can have my different products. So I can also look at D being the lever arm as R sine theta. And if you want to go back in your book and really look at this, this is going to be figure 8.4. So figure 8.4. Okay, and we talked about that. So now let's kind of work a problem. We're going to go back to our hunky-dory teeter-totter here. So I've got This is going to be point P. This is 2L, and this is L. We're going to apply a force. Here's our angle, and this angle is equal to 60 degrees. And we're going to apply a 25 Newton force. What we want to know is what is the magnitude and direction of the torque about P if L is equal to 1 meter. All right, so let's look at this for a second. Okay, we want to look at it for a second because we're going to figure out the direction without doing a calculation at all. The force is going to go this way, so we know that I'm going to get a rotation this way. So I'm going to get a clockwise rotation. If I take my fingers and I curl it in, I'm going to be going into the paper. And we usually refer to this as into the paper as negative. So my torque is actually going to be negative. It's going into the paper. We've used the right-hand rule to get there. If I look at it and break this up just a little bit, I've got my 2L. I have my force being applied. So I have the force. I have this angle and this angle are the same if you remember your geometry. So this is going to be F sine of the angle, and this is F cosine of the angle. This is the force parallel. This is the force perpendicular. Torque is going to equal my distance times the force times the sine of the angle. When I'm looking at my magnitude. This, as we said, L was 1 meter, so the distance is 2L, so that's going to be 2 meters. I've got 25 newtons, and that's times the sine of 60 degrees. And that's going to give me 43.3 Newton meters. And remember, that's not a joule in this case. That's strictly going to be Newton meters. And in the English system, like I said, we actually make it make sense, and that's foot pounds. I think we started talking about the first condition of equilibrium because we kind of did a wrap up of where we've come. And the first condition of equilibrium said that I didn't have any motion, so the sum of the forces had to equal 0. But now we're talking about rotation. And we've looked at these before, and we've played with these before, and you actually did it in lab. I'm going to do it as the teeter-totter. So I've got a plank. And I've got a fulcrum here, and I have a mass here, and I have a mass there. And we know that in order to be in balance or in equilibrium, if we assume that this is a uniform plank, first thing that we know is in order to balance our uniform plank, because this is what we have done over and over again, we know where we're going to have to place that fulcrum, right? If this is uniform across, this is going to be the length of the bar over 2, and this is going to be the length of the bar over 2. Because we've played with that. We know that. We've played with it over and over and over again. So if I know the mass of this one, and this is at L over 2, and it's imperfect, and when we say the mass of this is 100 kilograms, we know that if we're in perfect balance, the mass of this has got to be 100 kilograms. Because we've been playing with that since we were little itty bitty kids. Now the question comes is this. We're going to disregard the mass of the teeter-totter here. So we're not going to worry about the mass of the teeter-totter. But now if I put the fulcrum here, and I put a 40 kilogram object here, got a 40 kilogram object here, and this is going to be, we're going to call this L over 3. So this is going to be, so that's L divided by 3, and so this is 2L divided by 3. We want to know the mass that we have to have here in order to balance it out. So what we know on this case, so because we've played with this before, you guys have done it in the lab, we've played with this before, the torque on this side has to equal the torque on that side because they have to counteract. Because if I have the force applied here, this side's going to want to rotate that way. If I have the force applied over here, that side's going to want to rotate that way. The magnitudes better be equal, and we've got to keep track of which way we're at. So if I'm looking at this, we know what the force being applied is, because the force is going to be the mass times acceleration, which is going to be mass times gravity. So this is going to be 40 times gravity. This side is going to be whatever mass we need to know times gravity. And in this case, we've got, I don't have to worry about the angle because this is all being applied perpendicular, right? I've got the max torque that I'm going to have perpendicular. So this side is going to be my 40 times gravity times my distance, L over 3. This side is going to be the unknown mass times gravity times 2 times the distance over 3. My gravity and my length cancel out. And I'm going to do my 3 times 40 divided by 3 times 2. This one is going to be 20 kilograms is what I have left. So I could put a 20 kilogram box over there and have it balanced. Yes, ma'am. The 28th. No, it's the 28th. Yeah, it's the Wednesday after Thanksgiving. Thank you, ma'am. I appreciate it. We're all confused this week. It's just been a crazy week. So we've got 20 kilograms. So what we've got here, this is known as the second condition of equilibrium. And that says that the sum of the torques have to equal 0. The first condition of equilibrium is the sum of the forces have to equal 0. The second condition of equilibrium is that the sum of torques have to equal 0. And we can use that to our advantage, and we can play with it over and over again. So we have actually played with that. So I could do one here. Let's do another problem that looks like this, because I've got it all written out, and I'm at that spot in my notes. I could come back to it. So now, this time, I've got a teeter-totter that we're going to ignore the mass of the plank. I've got one mass over here, and I have one mass over here at the other end. So this is mass 1. Mass 1 is going to be 2 kilograms. Mass 2 is going to be 6 kilograms. And we want to know where we want to put this. This time we want to know where we're going to put that in the middle to balance it out. And this is your classic algebra problem. Okay? You guys have done this algebra problem I don't know how many times. If we tell you that the whole length of the beam is 5 meters, I want to know where I got to put that in order to have it work. So this is what we do. We say, all right, we're going to do that. We're going to place that one at X away from the meter, or from the end, and this will be 5 minus X from the end. And we can do the sum of the torques, this case, although they never gave you that as your problem. But on this side, the torque is going to equal 2 times my mass, or times gravity. I'm just going to go ahead and leave it as gravity, times x. That'll be the maximum torque. So that's the torque due to mass 1. The torque due to mass 2 is going to be 6 times gravity times 5 minus x. Those two things have to be equal because they got to balance each other out. So I'm going to get 2 gravity times x is equal to 6 gravity times 5 minus x. So I'm going to have 30 times gravity minus 6 gravity x, 2gx. Take this gx is on the other side. So now I'm going to have 2gx plus 6gx has got to equal 30 gravity. Gravities all cancel. So I get 2x plus 6x is equal to 30, or I get 8x is equal to 30. And now I get x is equal to 30 divided by 8. Whatever that number happens to be, because I didn't bring my calculator. What do we got?
3.75.
3.75 meters. Which is why we do it as a classic algebra problem, because it's how do I figure out the distance? Usually they give you the weight and they say how do we're going to balance it out. But again, conceptually, this isn't all that difficult. Conceptually, we know where we have to put, and we play with it because we've done this before, right? If I take my pin and I look at my pin, I know where I've got to put that pin in order to balance it. It's not directly in the center because the cap has got a different mass to it. It's not uniform, but we sit there and balance it. Because I know all of you have balanced forks at the dinner table. You've all balanced butter knives at the dinner table. You've all balanced spoons at the dinner table. And when you're little kids, you not only balance spoons, you balance spoons filled with mashed potatoes. We've all done it, right? We've all totally done it. And even if you don't want to admit it, you've done it, right? So we've all done it. We know where we're balancing it. So the question now comes is why, and how do I know, why can't I balance it like this? Let's see if I can get it balanced again.
Get the 5x and the x from.
The 5 is the length of my beam. And we don't know where we're going to put that, so we're going to set one side at x. And so the difference is 5 minus x. So the question was, where did we get the 5 minus x from? Okay. So the next question is, why can I get this to balance? And of course, now I can't get it to balance at all. That's always the case, right? So the question is, why can we do that? Because we've all seen Roadrunner, Bugs Bunny Roadrunner cartoons. We've all seen pictures of things that look like this. I've got the cliff, right? Here's my cliff. And I've got this big freaking rock that hangs out over like this. And it doesn't fall. And the question is why? The question is why? Well, what happens is Newton says this. Newton says that no matter what the shape of my object is, that the force due to gravity is going to act at a certain point. And that certain point is what we call the center of mass. And for my rock, as long as my center of mass is over the edge, it's not going to fall. Okay? As long as that center of mass is being supported, it's not going to fall. Just like my teeter-totter, as long as my center of mass is over the middle, it's not going to fall. It's totally not going to fall. So we've got that part that it's not going to fall. Now, we know that if I have a distribution that's not the same, so like this end is much heavier than this end, we know that my center of mass gets shifted and I have to make an adjustment for it. And if I'm in the physics lab, I can do this demonstration, and it's pretty cool. So I have a table, okay? I have a table, and I'll put my physics textbook on here. Okay, there's one physics textbook. Its center of mass is and we know, if we can say that it's uniform throughout, we know about where that center of mass is. It's halfway on the length side. It's halfway above the height side, and it's going to be in the middle, because if I look at it like this, my center of mass is going to be in the middle. I can put another physics textbook over here. Yeah, it's going to shift my center of mass, but I can still balance it. I'll put another one. Still have it balanced. Put another one. And now I've got one that's about the center of mass is overhanging on the other side of the table, but the whole system doesn't fall. I can actually get one completely off, and if you've ever seen Frank Lloyd Wright's, one of his houses, you'll see that you get this house that looks like it's defying gravity, but the reason is I've got it supported, and the center of mass of the whole system is still above the tabletop. So it's still being supported. So our two conditions of equilibrium are this: that the sum of the forces have to equal 0. What this means is that my mass times acceleration, this implies that my acceleration has to be 0. The sum of the torques is going to be similar, and we're going to talk about our rotational angle has to be 0. Now, what we're about to see is that torque can also be defined as something called I, which we talk about moment of inertia. Moment of inertia, and it's multiplied by the angular acceleration. Now, moment of inertia we've played with, because if I have a bicycle wheel, because this is usually how we play with it, we got our spokes. Once that thing is rotating, it's really, really hard to stop it. Once I get something rotating, it's really hard to stop it. If you've played with a John Deere baler, or any baler, the square baler, has a big, huge freaking flywheel on it, that flywheel is really, really tough to stop. When that gets in there, it's really tough to stop. So we actually use discs to help store energy for us. That's why we have the flywheels in there. That's why we do those things. So we get, and that moment of inertia is related to the mass in rotation. So we're going to get related to the mass in rotation. So the big thing is we got to look at, this is the center of mass, or we can call it the center of gravity. Okay, we got center of mass and the center of gravity. And we can actually figure these things out depending on what we have. And basically this is how it works. So I'm going to draw a big weird object. So I got a big weird object there. And I can take little teeny tiny masses I've got little incremental masses that are all being acted on by gravity. And even though you never have really done it, if this were a uniform glob, let's say it's a wad of bubble gum, okay, it's pretty uniform. It doesn't matter, each individual one of these little pieces is going to have about the same mass to it. We can intuitively, because we've played with stuff before, we can intuitively say, given this, I can look at it and I can do bisections, right? I can cross it around. And it's most likely that my center of gravity is going to be someplace right about there. So we can eyeball it. We actually can use symmetry to help us out greatly. If I have a block, and it's a uniform block, we know the center of gravity is going to be about right there, halfway, and if I'm in the block here, it's going to be halfway down the block. We actually can spot it without doing a single calculation, because we actually are looking at it. So I can do this, but I can look at this point in terms of its x distance away, and I can look at this point in terms of its y distance away, and I can look at the sum of the forces times the x direction divided by the total sum of the forces. I can actually get those. Get the equation that I want. Or this is if I want to do it with weight. Okay, that's if I want to do it with weight. I can do the same thing with mass. And basically what we say is that the x center of gravity, so wherever I'm doing it for my x position, is going to equal the sum of all the masses and their x locations divided by the total mass. I can do this for the y one, same way. It's the sum of the masses times their y location divided by the total mass. And I can do it for the z location. It's the sum of all of these divided by the mass. Now, for those of you who, this is how we do it in the algebra base one. But guess what? If I want to go to calculus, all the sum is it's going to be the integral. Just so you guys can see what that's dm, this is dm. So you guys can actually see where the calculus comes from. So now you can see why they came up with calculus, because it was a lot easier than doing all the little itty-bitty incremental little pieces. Totally incremental little pieces. So let's look at one of these. Let's find the center of mass of a problem here. So I've got, and the center of mass doesn't necessarily have to be on the object, because we've played with these before too. We've all seen mobiles, right? So I've got I'm going to make a fish mobile here. Got a real biggie fish, right? Got a big fish. And now we've got it chasing littler fish. And I've got something hanging down here, and I got lots of littler fish. But I don't have rotation because I've got the center of mass balance, and the center of mass is going to be somewhere along this axis because it's being balanced over here. And I've got it that this side, the masses on this side have got to be balanced with the masses on that side. So I've got lots of pieces there. So we can look at it. So what I'm going to do is I'm going to take a big mass, M1, and this on my handy dandy chart, because I'm going to graph it here so you can all see it. This is going to be at 0 and 0.9. And it's going to have a mass of 0.5 kilograms. Now I've got another little mass. This time it's over here. And this distance is 1.2, so its position is 1.2 and 0. This is M2, and its mass is going to be 0.25 kilograms. Then I've got one out here, and this is at position 1.5 and 0.3. And it has a mass of 0.15 kilograms. So let's look at this. The combined mass of these is 0.4, and this is 0.5. So we know that the center of mass is going to be closer to this one than it is going to be those two. And we also know, if I have this drawn to scale, because this is 0.4, it's going to be closer up here than it's going to be to the other one. So it's probably going to be somewhere in this area. We know that this is going to be our location where we could probably, if we tied all of these things together, that's going to be the location of where that center of mass might be. So let's actually calculate it out. So when you guys are working these problems, kind of think through them, because you guys, and don't overthink yourself, because this is very practical stuff. So we're going to find x sub c, and we're saying that x sub c is the sum of the masses times their x position divided by the total mass. So let's figure out the total mass. The total mass is going to be 0.5 kilograms plus 0.15 kilograms plus 0.25 kilograms. And that gives me 0.9 kilograms. So my total mass is 0.9 kilograms. I'm going to need that all the way through. So my x sub c is going to equal 1 over 0.9 kilograms times their individual positions. So my 0.5 was located at 0x. My 0.25 was located at 1.2. And my my other one was at 0.15, and it was 0.15. Now, if I multiply all that out and calculate all that out, I get 0.525, and this is in kilogram meters, divided by my 0.9 kilograms, and that gives me 0.583 meters if I've plugged it into the calculator correctly. Yep, distances were in meters. And now I do the same thing for the y direction. But now I got to do it in terms of my y's. So I got my 1.9 kilograms. The first one is 0.5 times 0.9. The second one is located at 0. So that's my 1.2 times my 0. And the third one is located at 0.3 and 0.15. I need somebody to put that one in the calculator. So I need this in the calculator. That's 0, so we don't have to worry about that one. This is 0.45. By 0.045. .3 times 0.15 is 0.05045, right? Add 0.45 to it. And give me the number.
0.495.
0.495. Take the 0.495 divided by 0.9.
0.55.
So that's 0.55 meters. So our X direction, if this is drawn to scale, is going to be at about, there's my X at 0.583. There's my Y at 0.55. And so my actual position is going to be 0.583, 0.55. So we can calculate centers of mass. So we can calculate those center of masses. And now we can use it to our advantage to look at the conditions of equilibrium. So, we've seen this a lot. We'll have a bar hanging off of a wall. We have a guide wire on our bar, holding our bar up. And we have a force due to gravity associated with the bar. And then this is a pivot point, and we're going to call this O for our pivot point. We're going to use this, how do I want to do this? Okay. We've got our force due to gravity here. We have a location W here. We're going to use this angle is 60 degrees. Yep. And then we are going to have a couple of forces here. And this is going to be a 45-degree angle, and this is the force O. And this is a 45-degree angle here. And we want to determine the tension here, and we want to determine this force in order to keep the bar right where it is. We're going to tell you that the force due to gravity is going to be 40 newtons. Force due to gravity. So basically what we want to do is we want to have this in equilibrium, not going anywhere. We want to determine the force that's being applied here at O, and we want to determine the tension in the string. So the thing we've got to do is we know that we have the sum of the forces have to equal 0, and we know the sum of the torques have to equal 0. I'm going to switch colors here so that we can keep track of the colors. Because my force here can be broken up into two parts. This is the force OX. This is the force OY. And OY is going to equal the force sine of 45 degrees. Force OX is going to equal the force cosine of 45 degrees. So we'll have that. Tension here, I've got tension X, except now my tension's in that direction, and I have tension Y, so there's my tension X. Tension X is going to be the tension cosine of 60 degrees. Tension Y is going to be the tension sine of 60 degrees. So I'm going to get several equations that I can play with, because what I can get is this. Sum of the forces in the Y direction have to equal 0, which is going to be my tension in the Y direction minus my force around Y minus the weight of the bar. Minus the weight of the bar. One other piece of information I need to tell you that this is 0.3 meters away. Because we're going to need that in a little bit. I think. I was looking for the value for, yeah. And this distance right here, from where our object is being operated, is 0.08 meters away. I needed to give you some distances. But I don't need them for my forces. I need them for my torques. Force due to X is going to equal 0. This time I get T of X, and that's minus T of X plus FO of X. So we know that the tension in X has got to equal the force on the X direction. So the T cosine of 60 degrees has got to equal F cosine of 45 degrees. So I know that T is going to equal F cosine 45 degrees divided by cosine of 60 degrees. So that's one equation that life has got me better. Now, so I've got this one. So if you plug in those numbers, oh, I've got the other one. We'll get it here in a second. Or if I do it this way, if I get F is equal to T, and that's cosine of 60 degrees divided by cosine 45 degrees, that actually equals 0.707 times the tension. I just had it in my notes backwards. So now let's look at this one. Ty is going to be T sine of 60 minus the force sine of 45 minus the weight of the sine has to equal 0. Okay. Now if I plug in for F, I get T sine of 60 minus 0.707 T sine 45 degrees minus 40 has got to equal 0. I can plug in numbers. I get 0.866 T minus, that actually is 0.707, 0.707 T is equal to, or minus 40 is equal to 0. This becomes 0.866 T minus 40 minus 0.5 T is equal to 0. When I do that, I get T is equal to 109 newtons. Now, if I got T is equal to 109 newtons, I can plug it in there, and I find F is equal to 77 newtons. Now, this required me knowing the angles. Okay? This is why I'm going to show you this problem again. This required me knowing the angles and knowing the angles on this force. But most of the time we don't know that, which is why I can do the torques. Okay? Because now if I want to know tension, in this required me knowing the angles of the force, but this time I want to know tension in the wire, I can do the sum of the torques equals 0. And now I'm doing the torque about O. Okay? The torque about O. And that is going to give me, if I'm doing that, I've got to have that the torque of, or the tension in Y times its distance away minus the weight times its distance away has to equal 0. I can solve for Ty because now Ty is going to equal the weight times 0.3 divided by 0.08, which is going to be my 40.3 divided by my 0.08, and that's going to give me 150 newtons. Now I can use the sum of the forces in the y direction, which has got to equal Ty minus Fy minus the weight. And now I've got that this is 150 newtons. We don't know Fy, but we do know this one. This was 40 newtons. That means Fy has got to equal 110 newtons. So now you can play with it a couple of different ways. And for those that want to end up doing mechanical stuff and mechanical engineering technology, that kind of thing, statics, the study of statics is all about the sum of the forces equals 0, the sum of the torques equals 0. We spend a whole semester doing those kind of problems. Spend a whole semester doing those kind of problems. I'm going to stop there because brains are full. I don't want to do moments of inertia and other rotation stuff just yet. We'll do that on Friday.
You heard about the Starfighter project?
No, I haven't heard about that one. No, the one I have heard are the two Harvard scientists that think that the comet last year